Okay, hi everyone. So, I think I could probably break it. Okay, I'll call on whatever mechanical engineering abilities I have later on, but it looks a bit busted. So, yeah, no one sits between you two. Okay, so I'm trying to head towards wrapping up multiple regression. It may take a bit longer than I thought. It's pretty loud. Anyway, is that okay with volume? Was it a bit loud? Okay. All right, so I've done a little bit of basic multiple regression in this example, and the things to note really are that a lot of things are not significant, but that doesn't mean that they're no use in prediction. So significance testing is just, does it seem different to the effect of the price of tea in China, if that was measured and put in there, is it any better than that? And if it isn't particularly, then it doesn't come up significant. So if it's totally irrelevant, it will not be significant, and if it's not quite shown it's relevant, it'll also be not significant. But that's very dependent on sample size, not to get too excited by. So if you need a scientific conclusion, you need to talk about significance. If you just want predictions, it's not as important. And if you're getting improvements in R squared, you're probably going to get improvements in prediction quality. And for those people who mentioned before that you should probably test prediction quality by a test set, I completely agree. If you had enough data, you could save some data for that, and Slava will talk a bit about cross-validation. And I'm happy to talk to people about it too, but I think I'll mainly leave it to him. Is the lecture up? The new stuff? Yes, I've just put some stuff up, but just very recently. I'm not going to cover all of it, but I just want to pick something out of it. Multiple regression? Something like that? Yeah, I've popped up a new file today. Yeah. But I'm only going to do a little bit of it, but a difficult bit, depending on your background. Okay, so I think I've said most of this stuff. The other thing that's important to realise is that the explanatory variables are correlated with each other. So this shows the levels of correlation of some things with each other, and it's pretty substantial in every case. So most of them have got an element of how bad is your stroke in them. So that's some collinearity. And in the old days, people used to try and avoid having collinear variables. And we still try to avoid having variables that have strong collinearity, but weak collinearity, so some level of correlation between variables is tolerated. And you can leave some variables out if you think they're measuring the same thing as something else, and hence collinear. But regression will eventually do that anyway. It will find the variables that are the best predictors of the response and ignore anything that's similar but not quite as good a predictor, once you put them all in together in the multiple regression. Okay. So, yes, I guess the only conclusion for that study was that while speed of admission is needed, you can use other motor scores to further improve predictive accuracy. That was the main point, I guess. And if you use just 2 variables, it's only a little bit less accurate than if you use all the variables. But I mean, it's 33% adjusted R squared versus about 47% with all of them. So that could be substantial, but we've left a fair bit unexplained. Chances are a lot of that unexplained part is just things that we don't have the data for. I mean, the variables we measured weren't sufficient. Yes?
Can I get an idea of how we get the adjusted R squared from the R squared? What is the...
I haven't got a slide of it, and I've kind of forgotten the exact detail.
Is it like a formula?
Yeah, it's just a formula. It's a fairly simple adjustment based on the number of variables going into it. I'll find out and include it. Yeah, you're right, I should. Sorry. Yeah, I can show you that. R squared itself is just based on a ratio of variances, so it's just a slight change from that. Yep. And you can even think of doing an R squared. For those of you who do like to think about test data, you could calculate R squared on test data, and that would be probably a better adjustment. Do you know what I mean? Like you use it, build a prediction model on training data, calculate the R squared on test data alone. That would be a perfectly valid R squared. There'd be no need to adjust it further. So either adjust it to try and take account of the fact you've used the training data twice, once for training and once for evaluation, which is a bit of a no-no, tends to introduce bias, but we've done it. So you can make an adjustment, try and fix that, or just use it on clean test data, and then it should be fine. Yeah, so this isn't ideal to be just doing it on training data alone. Okay, so I will criticise this as a measure later on a bit more, but you need something better really, but adjusted R squared is as good as we're going to do for now. Okay, I think this was just really a bunch of summaries. Yeah, I don't think I really had a lot of other points in that. Okay, so I got a question the other day about least squares, and I had made the claim that least squares regression corresponds to maximum likelihood estimation, and I tried to give it a quick answer to it, but it's not really a quick point, so I think it's somewhat important. I was going to cover it a bit later, but I think maybe now's a good time to talk about it. So, sorry.
What's the difference between multiple linear regression and the normal linear regression?
Yeah, there's a bit of a range of words, okay. So simple linear regression means one x variable, one y variable, linear equation with errors and all that. Multiple regression just means there's multiple x variables. But that's also called a linear model. So it has a number of names, yeah.
So if we use more than one variable, then it's called multiple linear regression.
If there's only one y, sorry?
If there's more than one variable, then it's called multiple linear regression.
Yeah, that's right. Well, I don't know if it's the only difference, but it's the main difference, yeah. It's a bit funny, okay. Right. So yeah, I'll throw the words around a bit sort of freely because they all mean the same thing. So multiple linear regression equals a linear model, and it can have one or more x's. Okay, so it's the general case. But there's no non-linearities in it so far, yeah. Okay, so these are some other notes. I just put them up recently. I'm not going to cover all of them for now. I'd like to come back to some of it, but it's really just still about multiple regression or the linear model. But there's a bit about likelihood I'd like to talk about. So I'll try, if I can remember. Okay, the view, yeah, full screen mode, okay. So this is partly based on stuff by Alan and Slava. Alan Huang teaches some related courses and a bit of an expert on GLMs in the department. Okay, so this is sort of revision, I guess, intended to be, but I don't know how much you know exactly. So how much do you know about likelihood? Have you ever maximised a likelihood before? You go, yes, in Data7202 L2? Okay, good. I thought you might have. Okay, so Just as a recap though, the likelihood function is a function of the parameters. So it's thinking about what will happen if we change the parameters given our data set is now fixed. So we've measured some data, we fixed the data set, and we're thinking about trying to fit a model to it and varying the parameters to get a good fit of the model to the data. So, but it's also defined as the product of the density of the data given the parameters. I guess I haven't written given the, but so the density function normally thinks of the parameters as fixed and the data as something that varies. And this switches it around a bit to say, no, we've fixed our data set, now we want to think about varying the parameters to fit the model as best as possible. But it's still a product, so a product of over all n observations in your data set. They can be multivariate observations, so a vector, or they can be a single value. But let's think of it in general as a multivariate observation and a whole bunch of parameters, as many as you need to define the model. And you presume there's some functional form of the model as well. So this would be known, this density function. And it implies a stochastic model, so we're going to assume that for now. You can't do likelihood without a stochastic model, that is with a random component. Anyway, then you normally take logs, and we turn the product into a sum. Any idea why I might be taking a log? It's addition rather than multiplication, and the numbers tend to be a bit smaller. That's probably a very good reason, yes. And if I'm maximising it, what's the effect of taking a log? Well, if I'm trying to maximise this with respect to, so I want to get the maximum value of this function, I'll find a parameter set that gives me that. What's the effect of taking the log? There's a whole bunch of answers here. Okay, let me try over here. Yes? Did you say monotonic? Yeah, that's right. Monotonic increasing, so it doesn't change the location of the maximum. And so it's fine to do that because it's convenient. Yep. You can maximise either one, but numerically this will be a better thing to maximise. Okay. So, yeah, there may be more than one, I guess. It doesn't have to be unique, the maximum, but there should be a maximum somewhere. It could even be local maxima, which wouldn't be much use. It's the value of the parameter set that maximises this function or the log likelihood. Either one is fine. Okay, so you probably know all of that. Don't really want to dwell particularly on that, except to say that MLE has a number of good properties. By the way, the phrase MLE refers to both, or to at least three things. It refers to maximum likelihood estimation, so the process of trying to find the best set of parameters. It refers to maximum likelihood estimate, which is the single set of parameters that have been found, and the maximum likelihood estimator, which is the random result of a maximum likelihood estimation process before you've measured the data. Okay, so I'll just use MLE whenever it sort of seems to fit, and you'll have to work out which one it is, but ask me if you're not sure. Okay, so it has a number of good properties, main ones being it's generally consistent, so it will approach the true value of the parameters. That is to say, we assume the data has come from, okay, this does make an assumption that the data has come from the model form that we've got, which is often not true. But so if that were true, if it was true that the data had come from the model we have with a set of parameters that we don't know though, and we want to get those parameters back by estimation from the data, if we use maximum likelihood estimation, we should get them back as long as our data set size goes to infinity. So that's not going to happen in practice, though with big data you get pretty close. So anyway, that's a nice property to have of an estimator. It's equivariant. I won't really get into that, but that's to do with functions of the parameters. It's asymptotically normal. That is only true for, okay, so it's multivariately asymptotically normal. That shouldn't really be 0, 1. But for a single parameter case, it's true. So it converges in distribution. And this lets you construct confidence intervals. The reason confidence intervals are easily available is mainly due to this thing. So it's sort of to do with the central limit theorem as well. Okay, so that's useful. It makes the theory of confidence intervals fairly easy, asymptotically anyway. So asymptotically as n goes to infinity. And it's efficient, which means it has the smallest variance of the estimated. So the amount of variability in your estimate is as small as it can be amongst all estimators, at least of those consistent ones. Anyway, I'm not going to dwell heavily on that. Yes, sorry. That's an estimate of the...
Yeah, you differentiating with respect to the estimated standard deviation. That is actually quite odd.
I have to admit I stole this slide and look at that very carefully. I know you divide by something to get this. I think it's the standard deviation of this estimator, which would be around sigma on root n. So S on root n type of thing. Yeah. So that's for a single single parameter. So it'll be, I think, the variability of the data divided through by a root n. I'll have to check on that. Sorry, I haven't got a definition to hand. I'll get back to you.
So does the theta n hat, is that just to say that it's sort of like n terms?
So you would have already estimated that as your... So that changes as n grows. That's why there's an n there. We've estimated... So that's the MLE estimate of it. And then we've got... I think we're taking out of that the sigma, which it must be for the data. So it's not particular... Yeah. It's just trying to say it's for the data set of size n. But I think there really is a bit of... Yeah, I think I should define that and I'll update it.
I think there might be a better way to write that.
I don't like it very much either. Yeah, it's a bit ugly. So I might write it separately and yeah, I'll change the slide, sorry. Okay, this actually wasn't particularly a slide I wanted to focus on, but yep, I should check it and fix it. Okay, I didn't want to dwell on that either, the regularity conditions, but there are some for this MLE stuff to work well. I didn't really want to cover that, but I can get back to it if those people want. Okay, so we can compute the MLE usually by just taking the derivative and setting it to 0. There's some conditions on that, some of which are covered here, but there's more really. For this to work, and so that will give you a flat spot of the likelihood function, or the log likelihood function in this case, but the flat spots are not necessarily what you want, because flat spots can be minima or maxima or saddle points, right? So the second derivative gives you the Hessian, and you can check that and see if it's negative definite, and if it is, then it should be okay. It should be a peak. All right? Doesn't mean it's unique or the global maximum. That's another issue. But you want the maximum to have that property. Do you know about negative definiteness of a matrix? Some yes, some no. Okay, so it's the opposite of positive definite. If you get a matrix, a symmetric matrix, a real symmetric matrix in this case, which they would be, you just check its eigenvalues, and if they're all negative, it's negative definite. Do I know a lot more than that about it? Some that I've kind of forgotten.
Really an important concept in this course.
No.
Because it's like I hear it from time to time, but I don't use it enough to actually remember it. I mean, it's like pops up and I don't use it for another year or two, and I've got to learn.
Yeah, I use it a bit more often occasionally, but I still forget it. Sorry, some of the details. So for a covariance matrix of any kind, you need it to be positive definite. Okay? So if you decide to make up a covariance matrix, you might want to check that it's positive definite. Okay, if it isn't, it's not a covariance matrix. All right, so that's important in sort of, if you want to simulate data and just make up a random covariance matrix, you need to ensure it's positive definite. So it is worth checking in those cases. So that's about the main case where I start to see it. And you can manipulate some things so they become positive definite. I know how to do that as well. But beyond that, I'm not using it that much, no. So it's a bit of a painful way to do it. I mean, you could probably do something more approximate and get an idea of whether this is a peak or not. But this is formally what you should do. Of course, you've got a big parameter vector, then this is a massive matrix and very slow to calculate, and you probably don't really want to do it. There's a guy in our department called Fred who studies second order optimization methods for neural networks, which is generally derided and not considered all that effective because it's a bit slow, but he's found ways to make it a bit faster, and I think it's quite good. But it does grow with the square of the number of parameters, this sort of matrix in general, so it's not something you rush to calculate if you can help it. But anyway, here we're just using it to check whether it's at a maximum or not, in theory. But that's usually, okay? So it doesn't always work, this. Have you seen examples? Oh, you've done a course with Thomas, I would have thought he might have covered this. He did? Yeah, okay, I think you might have. Anyway, some of you may not have done that course. But anyway, the problem is if you're doing a maximisation in an area of a function, the real problem is the following. So if I want to maximise a function, then I have this, that's my x-axis, let's say, or my theta, and here's the f of theta, and I want to maximise it. My function may be only defined over this region, from say A to B, and in that region it might do something like this. Okay, and then if I do the derivative, let's get this a bit brighter. Okay, if I did the derivative, I'd find this point, that one, and that one, and that one, and I'd probably work out that these ones were peaks, and I can compare the value at them and pick the biggest, and hopefully I found them all, and that's the winner. Right? But if the function then goes something like, instead, something like that, let's say, all right, then that would be the winner, all right, on the edge of the parameter space.
So you've got to check the edges as well.
Yeah, you have to check all the boundaries, which on one dimension is okay, because it's just a couple of points, but in high dimensions it's lines and planes, and it's quite a lot.
That's 784.
Yeah, anyway, it's a fair bit, so so you can't just assume that the derivative equals 0 is the answer, okay? So that's for a bounded one. If it's unbounded, you're probably more okay. But a lot of things are bounded, say at 0 or something like that. So bounding isn't that rare either.
Do they have efficient algorithms to work it out when it is on the boundary? Like to check the boundaries?
The boundaries aren't that big. I think you can search them.
I'm just thinking in machine learning, where there's an X.
It's a good question.
There's a lot of boundaries to check.
Yeah. I'm not really sure about that, actually. I think I've only considered cases where there weren't too many, but when there gets to be a lot of dimensions, that could need a special algorithm. Yeah, I'm not really aware of it, though. Sorry.
I'm sure that someone's got the solution.
I think it exists, yes. I think that's true. So anyway, the point is to check the boundaries. So yeah, it sounds like many of you have done MLE before. There's an example here with a Gaussian. So a Gaussian is about as easy as it gets. This is a one-dimensional Gaussian. That should be an X, sorry. It's in the range negative to infinity to plus infinity. So it's got two parameters, mu and sigma, or sigma squared. And you get the likelihood by taking that density, multiplying it up, the product, take the log likelihood, you get this, and then you can just do your derivatives, or partial derivatives, set them to 0, and it should work. And it works in this case because counts as something called the exponential family, which, again, I haven't got defined on these slides, but those of you who've covered it, it's a fairly common set of distributions are included in it. And for all of those, this sort of derivative technique works.
Were you going to do much on the exponential thing?
No, sorry. I'm happy to talk more about it if you want in person, but I haven't got much in the course on it, no.
I was just curious to know.
It's covered in the mathematical stats courses more. I think have you covered it in Stat 2x4? Or?
Yeah, we did a bit of that. That's why I was asking if you were going to go into that.
Not much, I don't think so. No, I'm just mentioning though that for things that meet those conditions, you can just do the derivative equals to 0 and that's it. There's only one maximum, basically. It's really easy. Okay, so you can get a solution for mu and for sigma via this method, and I didn't want to dwell on that particularly either. So yes, and some special properties of it. And okay, this was a case where things don't work out. It's as simple as having a function like this, and you try to maximise that. You have a likelihood that becomes theta to the negative n, and yeah, the likelihood equation becomes like this, and you're tempted to maximise it in the range, but the actual maximum value of it is not, well, you can't just set the derivative to 0, it doesn't work out. You have to maximise it through this. But again, I don't really want to dwell particularly on that, because I think many of you have seen that before with Thomas. But it's really just a boundary condition that's affecting things. So you have to check for a solution on the boundary at times. Okay, so what I did want to talk about was the regression part, not that bit either, that will come later. Okay, back to the simple linear model. So that's the simple linear model for regression with one x and one y. So we've only got two parameters in the regression equation, beta naught and beta 1, plus one more to describe the variance of the errors. So we've got some data like that, and we want to maximise the likelihood for this model. Okay, so it is a random model because we've got this random error on the end of it. Okay, so I want to extend that. So, well, first we'll deal with that model directly. So we've got the random y data here, and we've got the x data put into this form. So this is x1 up to xn, the n observations. And we put a 1 in this column because we're going to need to include the constant as well. We've got our two beta parameters over here, and the errors here for all the observations. All the errors will have the same distribution, but they'll all be different for every observation. Okay, so this is the model. yi is beta naught plus xi beta 1 plus sigma, sorry, is that epsilon I? And you can write that in this matrix form. Does everyone see how you do that? You've probably done it before. So you just take those two times this, plus that for the first observation, and so on, just down to n observations. So that's the linear model for one x variable. You can use the same linear model for any number of x variables. It looks like that in this case, right? So you've got a sum of different beta j's. We have to extend this to be, well, so we have lots of different beta j's and lots of different xij's. So for a particular observation I, we've got p different elements of the x vector. And you can write the equation like this, but this equation is just the same as this. It's just that this term is longer. We've extended beta from having beta naught and beta 1 down to beta p, okay, which is shown actually on the next page like this. Okay. So the x vectors have to be extended as well to have the full x data horizontally for each observation, and we just put all the observations down in the matrix. So that's the transpose there, putting them sideways, things that were originally a vector. So that's still x beta plus epsilon. So that's the way the linear model is usually written. Does everyone understand that? Yeah, okay. So the assumptions of linear regression are that these sigma i's are independent of each other, they all have a normal distribution, they all have constant variance. That's called homoscedasticity. And the number of parameters is p plus 1, because it's the p, or p plus 2 actually. It's p explanatory variables plus the constant plus the variance. So it should be p plus 2, sorry. Okay, but there's p plus 1 regression coefficients. Anyway, so rather than write y equals x beta plus sigma, and have to talk about the distribution of sigma, I want to write it like this. So y, the multivariate y, being all of the y observations from 1 to n, comes from a normal distribution with mean x beta and variance sigma squared times in. Now that looks a bit weird, but that's essentially a covariance matrix. Have you seen those before? Some nodding, some shaking. Who has not seen a covariance matrix before? I think, oh, okay. You've skipped a stats subject maybe. Or we have to catch up somehow. Look that one up, all right? So covariance matrix is like correlation. You've seen a correlation matrix, right? The covariance is just before you normalise it. So it's between all the variables, except the variables in this case are the y elements. So they're y observations from 1 to n. And they shouldn't be all that linked to each other, except through x, which they are. So this is really just trying to say that the covariance matrix is a diagonal matrix. So we have here the covariance matrix is sigma squared, sigma squared, sigma squared, all the way sigma squared basically, and that is of size n. And so since it's square, it's of course of n size this way. Okay, and all of this stuff is 0. I mean, there's not a big 0 there; they're just all zeros. Okay, zeros everywhere. And I just write it as a big 0 to indicate that. So the diagonal is all sigma and the rest is all 0, and that's because they're IID errors, all right? So that they're independent of each other. Because they're independent, there's no correlation, so there's no covariance. That's why their correlation and their covariance is 0. So it's just sort of a convenient form to say that in, really. But it's really just the same pretty much as saying sigma I, IID, normal 0, sigma squared. Okay, that covers the same point. Okay.
This is a multi-dimensional version of that.
Yeah, it's forcing it into a multi-dimensional space, but I was talking about y being of dimension n now, just putting all the observations in one thing. So it's a bit not that useful, but it jams it all into one line, I guess, mathematically. That's probably the main point of it. In terms of code, you would never do it that way. You would never put a matrix out like that. But in mathematics, it's neat that way. All right, so you can estimate. So that's the model, all right? That fully specifies it, I think. We don't even need to write IID here because we've only got one observation. This is all the Y data in one hit, one multivariate observation. Do you understand that? Given all the X data. Yeah. All right, so we can optimize the parameters of this using either maximum likelihood estimation or least squares. And I was trying to defend the idea that they were the same in this case because of the normal distribution of the errors. And it's not easy to, well, it's not super easy to show that. It's not that hard, but it's done here. It's kind of all done on one page, except for some of the details. So what I want to see particularly is if you follow, okay, so yeah, even the first line has skipped some steps. I thought I might say a little more about them. So I've got two screens. I'm going to take the risk of changing one of them. Good. Yep. Yes, I just don't know how that'll affect the recordings, but hopefully they're all there somewhere. Okay, so the basic thing, so I don't know if you know the multivariate normal density off by heart. A lot of statistics runs on normal distributions. Okay, it just assumes that, and the central limit theorem produces it in many cases, so loads of it runs on it. So you kind of need to know it eventually. So I sort of know it, but I kind of forget occasionally as well, so that's okay. But if we had something like y from a normal distribution with this situation, all right, so a mean mu, that'll be multivariate, so it's a vector. Let's say it's of length n, and this is n by n, so that's the covariance matrix. Then the density of the data, the corresponding density function, will be like this. Have you all done this before? Okay, good. Let me know if you're really bored. That's being a left-hander, sorry, yes. Also known as sinister, I think, but in some languages. But
We don't think that in Australia.
I hope not.
We know that you're all very bright.
Let's hope nothing sinister. Okay, so I will reveal it at times. Okay, so that's the covariance matrix, the determinant to the power half, and the bit up the top really that we're missing is the exponential form. All right, so that's an inverse of the covariance matrix. So it's worth noting that to do anything much with a normal distribution, you need an invertible covariance matrix, which is why collinearity is a problem. Because if you had two variables that were the same, the covariance would be 1, and you wouldn't probably be able, well, is that true? I think you may have problems with inversion anyway. And this is just the generally otherwise a quadratic form. Okay, so in our case we had sigma equals sigma squared in, right, the identity, times sigma squared, so that's a diagonal matrix of 1s, if you didn't know that, so it's 1 down to there, all right, size n by n, all the rest 0. So we need to get the determinant of that and take it to the power half, so well, that's just pretty easy. So we can just take the sigma squared out. I guess we could just have sigma there if we wanted to, times in, the determinant. And have I missed something? Got a bad feeling about this. No, I shouldn't have done that. I wasn't allowed to do that. Okay. All right, so yeah, so this matrix should actually look like, not with the 1s down there, I was getting confused on that, sigma squared all the way down. I mean, it was correct what I wrote for this, but when I take the determinant, I need to multiply all of these together. Like, you know, the sort of AD minus BC for a 2 by 2? It just keeps going and going, and all the rest are 0, so it just, you get the multiplication of all these terms. So it'll be sigma squared to the n, and then you divide by 2 again, because I've got that half as well. All right. So yeah, sigma to the 2n, and we've got this half, so that goes on there. I won't actually get rid of the 2. I'll leave it as sigma squared to the n on 2. So usually in statistics we estimate the variance, not the standard deviation, but it doesn't make that much of a difference, but we normally focus on the variance, which is this sort of thing, the squared. All right, so that's that term. And otherwise okay, the rest of the matrix, that's the determinant of the matrix, that's finished. Yeah, but it does appear again, it appears up in this part where we have sigma to the negative 1. All right, so we've got sigma squared in, okay, we've got sigma to the negative 1. Any guesses as to what that would be? 1 over sigma squared times anything? Yes, but it was only the one matrix anyway. Any idea what the inverse of an identity matrix is? Same thing again. Good. Yep, that's right. So that's all it is in this case. And when you multiply the identity matrix by anything, it has no effect. So this will sort of disappear from this term, leaving only 1 on sigma squared. So that's where the first line came from. Okay, that's why there's no sigma to the negative 1 in here. It's already been removed, and the sigma squared on the bottom is all that's left. Okay? So that is the likelihood equation for the linear regression model.
Do we have to be able to do this by hand, or do we just do it by
I'd like you to be able to do that by hand, yes. It worries me that you're struggling with it.
No, I'm not struggling with it. I'm just saying that it's going to be rather complicated having to do all those matrices.
Okay, more so for an assignment than for an exam. But let's see how we go with the assignment and see how that turns out.
Yeah, because I know I can do it, it's just going to be a bit time consuming.
Do it with what? Well, that is in LaTeX. Oh, I can do that for you if you want. But I don't really want to. Okay, so this is the correct form of this equation, and you can take the log of it. Powers come down, things go into brackets of a log. You get two terms here and all this sort of stuff. And then you take the derivatives and set them to 0. Now, derivatives with respect to a vector or a matrix are a little bit harder, and I'm not going to help you out particularly with those. I'm going to probably get you to do something on that for the assignment. But I don't mind you cheating off things like the matrix cookbook if you've met that before. So you don't really have to know exactly how to derive these matrix identities, but there's hundreds of them. So you don't need very much to do this. Anyway, the main point really is that this is a least squares situation, all right? So this is really just getting the difference between y and the predicted y, which is x beta. Okay, well, that's the idea, is we get the beta so that these predictions are as good as possible. We get the difference and we pretty much square it, okay? And effectively add them up over all the observations. That's what that matrix operation does. It gets the difference and squares it and adds them up. So the log likelihood has led to a least squares problem. That was the point. So, and it's all come from the normal, and it came from the normal because we had that identity, and this all collapsed to a least squares form. All right? That was a long-winded way to get there. You can take the derivative and set it to 0 and you get this solution. This is a very well-known solution for beta. And it all works fine as long as this x has full rank. If it doesn't have full rank, you start to be unable to invert this and it just all goes to hell. Sorry to say. The lasso can help with that, but you won't see that for a while. And people usually don't really care much about this term, but you can estimate it as well for a full model fit, and it comes out like this. Well, they do care, only if you're doing confidence intervals. You just want a prediction, you don't need it. So,
I'm used to doing both terms.
it's good to do both. Yeah, there's nothing wrong with it, but it's just maybe not as important to interpret. But if you want to get confidence intervals, you're going to need it. So, yeah. Well, there is a log here. So we did a log here and took all these terms down. Yeah. But this is just, so this was already an exponential, so having taken the log gets rid of it and it just leaves it on its own. So it's fairly, so there's no log left. So that's kind of good. It's another reason.
We can arrive at this, but just minimizing the least square, we arrive at the same formula without going through this.
Yes, that's true. Least squares just sort of says let's go straight to that and let's not worry about the derivatives or anything of a likelihood. So you could always do least squares. You can do least, I mean, people do least squares for neural networks as well, where there is no likelihood. That's fine. It's a good, but it kind of implicitly has a normal model. So if you assume there were normal errors on the end of a neural network, you'd probably say least squares is the right thing to do. If there was some other distribution, you probably should do something else if you cared about likelihood. So the main point of this was just to say that if you're doing least squares, you are doing maximum likelihood for a normal error model. Okay?
So is there a difference between least squares and maximum likelihood?
Sure. Change the error model, there'll be a different solution.
All right, so it's only if the epsilon is the error term, if the residuals are normally distributed.
Yeah, only if they're all normally distributed, that's right. If you change any of those details, it'll give you a slightly different answer.
All right.
The, yeah, I can't really say exactly what it would give you. It depends on what you've assumed.
I just want to know because I don't want to be in a situation where I use one as a substitute for the other.
Yeah, look, the MLE is the more general thing.
Yeah.
And least squares is just a special case of it. So least squares were studied first. It sounded pretty reasonable to a lot of people a long time ago to minimise the least squares as a way of fitting a model.
MLE is what you would do in a normal situation.
MLE is the sort of the main thing to do in statistics to optimise parameters. Yeah. So there's a fair bit packed in there. You may want to write that out yourself and sort of see if there's any steps that are unclear. Ask me about it if there's anything not quite clear.
What would happen if you did least squares, say, with the errors that were distributed binomially or something? Would that get bad?
Probably won't give you a consistent estimate, so it won't converge the true values. Probably give you some bias. Something like the variability might be higher than you'd like. Yeah, a bunch of those good properties will be gone. Yeah. How bad it is, I don't know. It would depend on the situation.
Don't take the risk up.
Yeah, MLE is what you want to do if you can in statistics. So, yeah, the least squares one, got a slide about that here. It's just minimising this, which is exactly the same as this format when you write it in matrix form and has the same solution. Okay, so I think I've run out of time for today. Got a bit of lab stuff to do tomorrow that we'll use linear regression models, multiple regression models, and you can try it in the lab or at home. The tutors will be around to help if you want. An assignment that's somewhat related will come out hopefully in the next week. Okay, any questions? You can talk to me now maybe. Yep.